Okay, I'm back, and in our previous segment, we were talking about how constellations are in different parts of the sky depending on the time of the day, the time of the year, and then also your location. So, in this last segment, we want to talk about how they can appear to be in a different part of the sky over thousands of years. So now we're going to talk about precession. And in order to understand precession, first let's talk about Newton's laws of motion. Now there's three of them. Later we're going to find out what all of them are. But for right now, let's just talk about Newton's first law of motion. There's two versions of it. So the first version is for an object that is moving in a straight line, and then the second version is for something that is rotating. So let's look first at something that's moving in a straight line. So it could be, let's say that you take uh, a, uh, a ball and you roll it on the ground, and it's initially going in a straight line. So Newton's first law of motion says that if there's no outside forces acting on it, it will roll in a straight line forever and ever at a constant speed. So its speed won't change, and it will go in a straight line. Now, in fact, it doesn't. So it slows down, and that's because there's a force acting on it. Friction. So that's what slows it down. So if there's no forces acting on an object, then if it's initially going in a straight line, it's going to continue to go in a straight line forever and ever at a constant speed. Now let's apply that to something that is rotating. So now let's say that you've got a ball and it's rotating around and around. Newton's first law would say it will continue to rotate forever and ever at a constant speed, and more importantly, the spin axis doesn't change direction. So you see the bar on this? That's the spin axis for the Earth. So if I turn this, you can see the Earth spinning on there. So that's the spin axis. So if there was no forces acting on the Earth, then the spin axis would point towards the North Star, Polaris, forever and ever, and would never change. But just like if you've got an object that's going this way, and it can be knocked off course when you apply a force to it, similarly, if you've got something that's spinning and you apply a force to it, it will change. Its axis will start to do this, so that's going to be called precession. So you see how the bar is going around in a circle like that. So that's going to be called precession. So let's look at precession of a top. So what I want you to do is watch this video here, Gyroscope by Science Online, to see how a top works, a gyroscope. And then I want you to watch this other video called Precession of the Earth. Have you watched them? I hope you have. All right, because that's going to help you here. So you saw that gyroscope. It was that very small gyroscope. They wrapped a piece of string around it. They pulled on the string. It started to spin. And then when they put it on the stand, did you notice that it started to do this? It was precessing. So the gyroscope was spinning very rapidly, but at the same time, its spin axis was actually going around in a big circle. So that would be the precession rate of the little gyroscope caused by a force. A force was changing the axis. It was the force of gravity caused by the Earth. Now the Earth, it also is spinning once every 24 hours and is also precessing, and because it's being subject to a force, the force of gravity of the sun. So as the sun pulls on the Earth, it causes the axis of the Earth to very slowly change. How slow? Once every 26,000 years. With that little gyroscope, it was maybe once every 5 seconds it was going around, whereas this, it goes around once every 26,000 years. Well, why? Well, how fast was the gyroscope spinning? Well, maybe once every second. How fast is the Earth rotating? Once every 24 hours. So that's one of the reasons why that the Earth precesses so slowly. Now later, in another lesson, we are going to talk more in depth about precession, and I'll even show you the formula that allows you to calculate the precession rate of an object, which I wouldn't expect you to be able to do it, but I have these formulas and I like to show them to you just to see what they look like. So that's precession, and what would it do to the constellations? Now, if you had a constellation that is located here today, and there's another one right next to it, well, 26,000 years from now, they're still going to be neighbors, okay? So the relative locations of the constellations are not going to change with respect to each other, but where they're at in the night sky will. So that, for example, one of the, we know that Orion is a winter constellation, so it only appears in the wintertime. Okay, now in 13,000 years, the Earth is going to be tilted like this, so it's because of precession, and so wintertime will be summertime, and summertime will be wintertime. So the seasons will be reversed, so that Orion will come out during the summertime and not during the wintertime. So pretty weird stuff going on here. So let's take a look at, let's do our review here. So what is the modern definition of a constellation? So it's not a picture. It's going to be a group of stars that are inside one of these puzzle pieces that contains one of the traditional constellations. A constellation seen on Earth looks the same to a person on the other side of the galaxy. No, because constellations are not two-dimensional, they're three-dimensional. So that the shape of a constellation will actually change depending on your viewing angle. Which is brighter, a second magnitude or a fourth magnitude star? Now be careful, because the ancient Greeks said the brightest star was the magnitude 1, and then they get progressively dimmer as you go down to a magnitude 7. Okay, so the second magnitude star is going to be brighter than the fourth magnitude star. What on Earth is similar to right ascension? So remember, you're either going to your right or you're going to your left, so that's going to be the longitude. What is the angular size of the moon? I'm sorry, that went with another slide that I have deleted, so just ignore that. What does precession do to the spin axis of the Earth? So it causes it to change, so that as the years go by, the spin axis of a planet will very, very slowly change due to precession. So that's it. That noise, that means that it's the end of our lesson for today. So next time, we're going to do like cave person science. We're going to look at what did the people very long ago, when they looked up into the sky, how did they explain what was going on, and then how do we explain it today using the actual motions of the planets and the sun. So stay tuned for that next time. Bye.